Okay, this video is for Team A, Capacitor team, Marco, Bryant, and Jessica. And our job for this part of your presentation is going to be to demonstrate that you are able to build a capacitor model using the ANSYS software. We talked about the workflow where we're going to create a structure, we're going to add the boundaries and excitations, we're going to set up the solution, solve it, and post-process. Post-process basically means evaluate your answer. And what's not shown on this flow is that if we don't like the answer, we might go back to the beginning and make some changes or changes in other places along the way to see if we get an improved result. Now, we're probably going to make connections between an analytical calculation. If you remember this in class, the value C stands for capacitance, and it's equal to epsilon, which is a material value, times the area of one of these capacitor plates divided by the distance that separates the two capacitor plates. So that's really as complicated as it gets for an analytical estimate of a capacitor. What we are trying to do is build a simulation model of the actual capacitor that we use on our crystal radio. So you certainly remember this. We all had this on our radio board. There was a knob on top of it where we could turn it from left to right about 90 degrees. And in doing that, you can see the values written here. We were going from a capacitance value of 0 to 532 picofarads. So the way, I guess the challenge that I gave you was, can we use ANSYS Maxwell to design a capacitor that's going to give us a value of somewhere between 1 and 532 picofarads and make a simulation model of that. So that's our objective. What I want to do right now is walk through the steps of building this capacitor inside Maxwell, and we're going to have a very focused attention on going through this workflow, because in your presentation we're going to want you to demonstrate that you know how to do that. So let's get started. Okay, the first thing we want to do to get started, even before we create the structure, is create a design type. So I'm in electronics desktop with nothing created. When I hit the new button, I get a project node that doesn't have anything in it either. Now I'm going to choose a Maxwell 3D design. When I do that, it pops into my project, and you can see all the familiar buttons that are connected to our workflow. You can see our 3D view area here, our project tree and our modeler tree. All these things are going to start to fill in. Before we start drawing the structure of the capacitor, you have to do one thing. You have to go to Maxwell 3D up top and change solution type from magnetostatic to electrostatic. Capacitor is designed to store energy in the electric field, not the magnetic field. That would be used for the inductor. So make sure you switch it to electrostatic, and now we're ready to start building out our capacitor. A couple of ways to do that. One quick thing that's very important is that we have to have an idea of what our goal is as far as meeting the constraints. So from a structure standpoint, from the geometry itself, we want to make sure that whatever we draw, the two plates, the sandwich material, and whatever's going to be in between it, we want that whole volume to reside within 1 cubic centimeter. So we can see right here we're operating in millimeters. 10 millimeters is 1 centimeter. So it should be pretty clear how we do that. And when we start using these objects here to draw, we'll see that we can manipulate some of the settings and the values in that modeler tree as well. So let's start by drawing out the bottom plate. It's a 3-step process. I'm going to give this plate a little bit of thickness, so it's not going to be a surface, it's actually going to be a solid. So I'm going to use the draw box function. So when I click this button, if you look on the bottom left down here in the corner, it's asking me to enter the box position. I'm going to drop it in the -x and the -y dimension, and I'm just going to choose an arbitrary location of a point. So I'm going to drop the first point there, And now it's going to ask me to enter the opposite corner of the base of the rectangle. Now I want this point to reside in the positive XY space. So that might be close, or good enough at least. And now the final thing it's asking me is to enter the height. And notice if I just raise it up, it looks like it's trying to snap to about that grid. Don't worry about the specifics at the moment, because as soon as I left click one more time, I now have this object called the box. I can see it's in the solid category. It's been given a name, box 1, that resides under a material that we have yet to define. So right now it just considers it to be vacuum. So that permittivity of that would be the same permittivity of the epsilon naught for vacuum. We're going to change that. Before we do, I want to make this 1 centimeter square. So if I create this box, if I select the create box node here, I can see in my properties panel that I've got a position, X, Y, and Z size. So if I want it to be right in the center of the coordinate system, I can just choose let's say negative 5 millimeters in the X. I'm just typing over the values there, negative 5 millimeters in the Y. And I'm going to make the plate, let's just say 1 millimeter thick. So I'm going to go negative 0.5 millimeters, and you'll see why. So I'm going to put a 0 in front, negative 0.5 millimeters. And my X size is going to be 10 millimeters. My Y size is going to be 10 millimeters. And my Z size is going to be 1. So let's just get a view. I can get the angle and point it out. So I can see that now it looks like it's centered in the Z-axis. And it looks like it's got 5 millimeters to the left, 5 millimeters to the right. So this appears to be the right size. And I can even use the ruler here to verify that that size appears to be right. So far so good. When in doubt, I can always right click and I can say measure, and I can choose an edge to measure if I wanted to. And that should tell me it's got a length of 10 millimeters. So that's also good. Whenever you do measurement, just make sure you get back, right click, and make sure when you look at selection mode should always be objects. Okay? So sorry, that allows me to select objects. You can always escape and hit the letter O, and now I'm in selection of object mode as well. So make sure you do that. Again, right click, selection mode should be on objects unless I'm trying to measure something else. Okay. Okay, we're still in the structure build phase. We have about 1/3 of our geometry. So what I want to do now is I'm just going to copy this, and I'm going to do it by translating. So pay close attention to these steps. The first thing I'm going to do is select the object, so box 1. And now notice there's a command called move, but right next to it there's another one that's called duplicate. So I'm going to duplicate along a line. So with that selected, I can see down in the bottom left it's telling me that I have one object selected. So don't do this unless you see that. And now I'm going to hit this button, and again in the bottom left it's asking me to input the first point of the duplication vector. It's hard to see here. I haven't selected yet. I'm going to choose. I'm trying to choose the origin. So I believe that's it. So that's the base of my move vector. I haven't selected yet. Again, I'm just going to let the cursor move the shadow of it. But if you look at the bottom left again, it says input the second point of the duplication vector. Now I'm just going to move it up. I'm going to slide it up. This. Okay. So I zoomed out. I haven't clicked yet. I'm going to move it up. That looks like maybe it's like a centimeter if I look at my ruler down there, something close. And I'm gonna click the button. So now it still is asking me for one final thing. It wants to know the total number. And it defaults to 2 as if I just want a copy, and I'm going to go ahead and approve that. So now that I did, I can see I've got a box 1 and a box 1_1. So they're both falling into this material called vacuum, and so far that's fine. There's a change that I want you to make that's going to be very handy. And if I break out the project tree here, and I think if I do it this way, it'll work. If I choose duplicate, maybe it's this one. Okay, no, that's it. So I'm going to choose the duplicate along line that's all the way at the bottom of this tree. So make sure you're selecting the right one, and you'll see the property panel comes up with the vector. And if you look at that vector, it's telling me that the vector has only a z direction, which makes sense. But what I want you to pay close attention. I'm going to type over, for me it's a number 4, for you it might be something else. I'm going to type over just that number, not the comma in front of it, because that's indicating the z direction. And I'm going to type in a word. I'm actually going to type in an expression. I'm going to type distance, capital D. I'll say distance, and I'm going to say -1 millimeter. So type that in exactly, and when you hit enter, it's going to give you an error apparently. Let's see what the error, character 8, 1, 2, 3, 4, 5, 6, 7, 8 is not a, it doesn't like the word distance as a variable. So I'm gonna change the spelling a little bit. I'm gonna make it dist C. You can make it whatever you want. You can make it your first name if you wanted to. So this is telling me the distance of the capacitor. And let's see if this works now. And it looks like it does. You can see the name of it up here, DISTC. The unit type, I'm going to fill this in. It's going to be, let's see if we can find it. There's lots of values here. It should be, is it going to be distance maybe? Zoom in and I'll see if I can find, I'm in the wrong part here. There, maybe it's length. Okay, right here. We have length right there. So I'm going to put in length. The units, I'm going to go ahead and keep the units as millimeter. And for now, let's just make the distance. Let's see what, 10 millimeters. Okay? And there we go. So now, by doing that, I don't really have to worry too much about doing that move command over again because I just created a variable. So now, let me show you how to change this variable. If I go to the top level Maxwell node here, notice when I click this object, in the property panels, I can see my dist C shows up. And it's got a value of 10, and I'm free to change this to whatever I want. So I can make it 5 now. If I make it 0, it's going to adjust. That's an invalid number actually, so don't make it 0. You're going to want to make it something more than 1 at all times. So actually more than 2 at all times. So you have to hold on to that constraint. This means they're in direct contact. So by saying distance -1 millimeter, I took into consideration the thickness of each of these based on that reference origin system. Okay, so the rule, if we use this, is that you always have to have a distance of something greater than 2 millimeters. So I would actually say 3 millimeters maybe would be the lowest we would want to go in this example. But you're free to make it 4 and 5, and you'll see it move accordingly. So I think you'll find that this is a lot simpler than in class when we did a duplicate, but every time we wanted to change the distance, we'd have to reapply that command, and it got a little bit cumbersome. So keep track of the rules. Make sure that when you apply your distance, set a value. you always are using something that's valid and it looks the way that it's supposed to. Okay? It's always a good idea to save as you go. Make sure you know where you're saving your project. I'm keeping mine in my default directory, and I'm going to come pull them all out later on. So I'm going to call this, you guys are Team A, so I'm going to call it Team A Capacitor. And I'm going to make this available to you in your folder. I hope that you replicate and you know, your own original design. Maybe you change the variables a little bit. But there we go. So far, this meets our criteria of at least fitting within that 1 cubic centimeter space. So we're 2/3 of the way done with our geometry, because the next thing that I want to make is a box that's in the middle. That's our dielectric, if you remember. That's the thing that's going to have the material associated with it. So let's think about how to do that now. I think we're gonna reference the same. We'll reference the same coordinate system. And let's just try this. I have a distance variable that's already set. So I'm gonna make another box. And I'm going to, I can reference actually the same box, can't I? Actually, I think the best way to do this would be to just pick off of the vertices that we see, given the 2 plates that we have. So it's waiting for us to pick our first point. So let me do that now. I'm going to choose the first point. You can see it wants me to drag and drop the second point. And now let's make the third up here. Now, another thing that I could do, I've got a dielectric. At least I have my third box. What I can do now is click on box 2, create box, and I'm going to change not the position, but the Z size to distance. So dist C was the variable, if you remember. Capital DIST. And as I start typing it out, I can see dist C is right there. And now it didn't change because it totally fits within the dimensions that I've given this. Now watch what happens when I move the variable. Now that I made the thickness of the middle material the same dimension as dist C, as well as the separation, actually something has happened here. Actually, I have to subtract out 1 millimeter because I had an overlap. Now, I have to subtract 2 millimeters. Does this make sense? When I subtract 2 millimeters, I don't have the overlap anymore. So, as distance moves, I built up from the top, and I'm subtracting out the thickness of each capacitor. So now let's go back to the Maxwell design here, and what happens when I go to 5 millimeters? It appears to adjust with it. So that looks good. What happens if I go all the way up to 10 millimeters? It looks like it's moving with it. So you can see I made a couple of incorrect decisions when I was setting this up. But you ought to always be able to verify that, yeah, my sandwich material on the inside is not overlapping with the top capacitor plates. And eventually we figured out we got the right variable connected. So I'm using one variable to control the separation, and I'm also filling it in with this new box, that dielectric. So makes it incredibly handy. And I think I saw Jessica was having some issues with the way the software was rendering for her, and it was very confusing. I think this is going to help eliminate that quite a bit. So let's see. So we have a geometry now. We have what's going to be the 2 capacitor plates, and we also have the center dielectric. So we're going to probably set up our materials next, I think, and then maybe move on to setting up the excitations, which again is part of our workflow. Just a quick check of where we are in the process. If you remember with our flow, we are still in simply creating a structure. We haven't left this part of the process yet. So before we add materials, I'm going to change colors. If you remember how we did this before, when you select the object, excuse me, when I select the object, I can go into the color here and give it any color I want. I'm going to go with a blue, and I'm going to also make the transparency something so I can see inside. So that's kind of nice and helpful. I'm going to go ahead and leave these the same color. That's fine. But now what I'm going to do is I'm going to dual select both of these plates. These are my capacitor plates. And now if I right click, excuse me, I can assign material, and we'll wait for the big window to pop up. And now I'm just going to assign perfect electric conductor, which we've done before. So I'm just going to type in PEC and hit enter. And look what's happened. If I collapse these out, it's a little easier to see. My two plates, box 1 and box 1-1, are both underneath the umbrella of peak. This is still defaulted to vacuum. And for our first run, we're actually going to be okay with that. We're going to go ahead and leave the dielectric a vacuum as if it was something like air. So we're not going to give it a specific material property right now, but it does have one. It's the permittivity of free space at the time being. So my materials are now defined. What I'm going to do next is define my excitation. So boundaries and excitations, I think in this case, I don't think I'm going to be putting any explicit boundaries in, but I'm going to be doing this with excitations, and there are some additional things that are kind of involved before we get to the solution setup. But let's do that next. So what I'm going to do for the excitation is I'm going to choose the top plate, and I'm going to right click and say assign excitation, and I'm going to give it a voltage excitation. And I'm just going to keep the default. It says voltage 1. I'm going to give this a value of 1 volt. I can probably type it in here and watch it update. So make sure you see a capital letter V instead of a lowercase letter, or I should say with a lowercase m in front of it. That would be millivolts. So 1 volt is what we want, and I'm going to say OK with that. And then on this plate, I'm going to give this a different voltage. So if I right click on this, I'm going to assign excitation. I'll give it a voltage, and I'm going to actually call this voltage 0 because I'm explicitly saying it's 0 volts. 0 millivolts is the same as 0 volts, so we don't have to worry about that. So I've got my voltage 0. I've got my voltage 1. It's telling us here what the values are. So far, so good. If you remember, a little different than some of the other simulations that we've done, in order to calculate the capacitance of this object, we actually have to define something in parameters, and it's called the matrix. If you remember, I'm going to right-click this and assign matrix. And when I do that, it's asking me which of these excitations I want to include. I'm going to include them both, and that's going to allow us to directly calculate the value of capacitance. So we're just going to say OK with that, and I'm going to save again. And now I believe we are likely in the analysis setup stage. So again, quick check. We added excitations. The matrix is probably somewhere in the middle here. We're going to go ahead and set up the solution, and then we're going to hit the verify and solve button, and then we'll look at the post processing. So analysis. I'm going to right click, choose add solution setup. And this convergence, basically these are settings that are going to determine the accuracy of the solution. Minimum number of passes, I think we talked about that in class a few times. I'm going to crank it up to 15 just in case. And I'm going to make the percentage error a little bit lower. If you remember, every time we do a pass, there's an evaluation of the elements in the solution. And it makes a decision. If the solution has not met the error criteria, then it will add more elements and continue. So sometimes we'll see the adaptive passes go up to a high number. And every time it does, it adds more elements, which makes the solution a little bit longer and makes the file larger. So we're trying to get a balance of that. So I'm going to go with these settings for now, 15 and 0.1 for the error. And I believe that's all we need to do. So I'll find out in a second when I try to validate it. So I'm going to save again. And we're now moving on to the simulation portion where I'm going to validate. You should get all green check marks. So that's good news. And now I'm going to hit the Analyze All button. And we're going to let the solution take place. This probably won't be too long. I paused while I solved, but I really didn't need to because I got a result very quickly. So you should see something like normal completion of the simulation. So that's great. That means that we are ready to look at the results. So I'm going to see if it's in, I think it's in electrostatic reports. And we're going to just go to data table. Let's try that. So when I bring up data table, I can see, let's see, the value C is for capacitance. Okay, so all this should be the same. We're going to leave that as default. And I'm going to plot capacitance in the category. I want to choose this value. It's voltage 1 to voltage 0. It should be identical to voltage 0 and 1. I can choose them both, or I'm just going to choose 1. It really doesn't matter which one you choose there, 1 to 0 or 0 to 1. Just don't choose voltage 0 on voltage 0 or voltage 1 on voltage 1. So with that, I'm going to leave the function. I'm not going to apply anything else there. And I'm going to go with new report. And I'm going to close this and see, it looks like I got a value here. Don't worry about the negative number right now. It's just because of a reference. So we're just going to treat that as if it was an absolute value and a positive value. But look at the small f in front of the capital F. So that stands for femtofarads, 1,000th of a picofarad. So we're not at the 1 picofarad minimum requirement that we were looking to get. So our geometry works just fine. We have 1 centimeter square plate that's less than 1 centimeter away from each other, both of the plates. So that fits within the volume constraints. That's fine. But we didn't hit our target. So we have decisions to make. How do we improve this? So there are a number of things you can do. And if you go back to the analytical estimate, we have a baseline value that's in the femtofarads. If we want that to get larger and hopefully get picofarads, there's a couple things that you could consider here. Could we change the area? Well, changing the area with our simple model is going to be difficult because we're going to exceed 1 centimeter in the X or the Y dimension. So we're kind of locked in on that. But the epsilon is referring to a material value. And we chose a dielectric of free space, basically. So we might find values that are much larger than that. And if you remember, in class, Anastasia calculated by hand what one of those values might be to be able to achieve some middle of the road value of like 200 picofarads or something along those lines. I can't remember what the exact number was. And we actually solved it and verified it in class by hand using this formula. We came up with an epsilon of 3,000. I believe it was 3,000. So we could play with that value. We could or we could also, you can see as you decrease the distance, the smaller that distance gets, it's in the denominator, the larger the capacitance will get as well. So I would encourage you to try some different things like change the material value or play with the distance. I'm going to give you a little bit of a hint on the material value right now and go through and make a change there, and let's see if we can get something close, and then I will let you take it the rest of the way. So what I'm going to do, so I can save our baseline design here, is I'm just going to highlight what's called Maxwell 3D Design 1. I'm going to copy it, and I'm going to paste it right into the original project. And now I'll get a new design. It's going to label it Design 2. The only reason I did this is because anything that I tamper with in this design I'm not going to corrupt the original design. I know I had a capacitor value that seemed to be solving, even though it's not the value that I wanted. My parameter was working out just fine. So if I mess anything up, I only have to mess it up in this design. No big deal. I can always recover the first one. So that's why I did that. All I'm going to do is change the material value to a different relative permittivity. So if I go in here and I look at vacuum where box 2 was, I'm just going to right click assign material, and I'm going to show you how to make your own material based off of an existing one. So if I say, let's say vacuum 1 right now, I just happen to be on vacuum and projects. I'm going to go to clone material, or let's do this. Yeah, let's clone the material. And when I do that, I have to give it a name. And I'm just going to call it material 1. You can call it whatever you want. Okay, there's no other material 1 in this database. I get to assign a relative permittivity right now. And that's the actual thing I'm trying to do. Remember in class we did 3,000 was our solution. I'm going to see what happens when we go for something lower than that, 2,000. And it's not bulk conductivity, it's relative permittivity. So there's a value, and I think with that, I'm just going to leave everything else. I'm not going to worry about all these other advanced settings here. But material 1, we know that it has an epsilon, a relative epsilon of 2,000. And I'm going to, don't forget to OK it. When you do, it should show up as material 1. And there it is. So now I'm going to rerun this simulation. I'm going to validate first, analyze all, and this is going to solve very quickly. I copied this design that already had a report in it. So as soon as it's done, which looks like it is, I can go to results and I can just double click that table. And look at how much my values have increased. Quite a bit. So by changing it from air of a vacuum to whatever 2,000 would map into, I've got something that's in the vicinity of what we wanted. We wanted something between 1 and 520-something picofarads. We're about halfway there. So that's pretty good. Pretty happy with that result. I think from this point on, you ought to be able to manipulate this capacitor design and see if you can get it to 500 picofarads, maybe by changing the distance, changing the material again, and build out your presentation based on demonstrating the steps in the workflow that we just went through. We went through all of those steps in the workflow, and I think there's plenty that you can cut and paste from this design to be able to put into a presentation and talk that through. There is one final thing we haven't spent much time on, and I thought it would be a really good idea to cover this. You might be able to include this on your presentation. So watch how I plot fields here. I'm back in my 3D view. We got a value that we like. I would like to maybe explain a little bit of the nature of what a capacitor is doing. And you may have heard us mention in class that it's known as a field storage device, the electric field. So when I break into the planes here, I'm going to choose, it looks like the global XZ or the XY, either one should be fine. Let's, XZ or YZ. So that's great. So what I want to do is I want a cross-section view. So I want a cross-section of going right through this capacitor, and I'm basically going to say, plot the electric field vectors on top of this plane. So that's all I'm looking to do. And I don't know if we ever really talked about what they look like. So let's find out. So I've got the plane selected. You have to have the plane selected. And then now when I go to field overlays, if I right click on field overlays, I can choose fields, and I'm going to choose E for electric field, and I'm going to choose, let's do E vector first. So all this should be fine. I'm not going to mess with any of this. I'll just say done. And that is exactly the view of the electric fields. We're getting a physical field value that we can measure with a voltmeter or the appropriate type of device, I guess I should say. But the electric fields are directed uniformly from the top plate to the bottom plate. So if I look at my excitations here, it makes sense. That's a positive voltage. We gave that a voltage of 1. So the vector fields are going to start from the high voltage and go down to the low voltage of 0. So all throughout that space, I've got an electric field that's established, and this capacitor is able to store that electric field, and it comes out in the form of a distributed charge on the plates or a voltage. So that's what that vector field looks like. So that might be worth including on the presentation when you talk about the radio and where the capacitor is and maybe what its job is. Okay, I'm going to leave you with this, and good luck, and I will see you on Tuesday.